Good morning, everyone. Thank you for joining Allison Bales and I today for our webinar on humidity control above, below, and in the house. We have people logging in right now, so we'll wait just a couple more, couple seconds, and then we will go ahead and get it kicked off. This is being recorded and will be available after the webinar. You should get an automatic email with the recording, but if you don't, please reach out to me and I'll happy to send you a link. And then also on the right-hand side there, you'll see there's two buttons. There's ones for questions and one for chat. If you want to make sure if you have questions, you put it in the questions section. And then we'll make sure that we can try to address those at the end. We have a lot of content today. And if we don't get to them, we'll try to capture them and make sure that we get back to you. Or again, you can email us as well. So with that, we're going to go ahead and kick off the webinar. And I'll be running the slides here for Mr. Allison Bales. Allison, why don't you go ahead and introduce yourself?
Okay, go ahead and click through the bullet points here. So,
okay.
As Nikki mentioned, my name's Allison Bales. My company is Energy Vanguard. We do a number of things: consulting, training. I write the Energy Vanguard blog, and I have a book out. You'll see in a second. And we do HVAC design all over the country. And so here's the book. It's called A House Needs to Breathe. Or does it? And the answer, I don't make you wait in the book very long for that. The answer is on page 23. You can buy it at energyvanguardstore.com. But if you're looking for a copy, don't go there right now, because at the end of this webinar, I've got a screen with a discount code, so you can get $10 off if you use that discount code before next Monday. And so that's coming up. Next slide. Okay.
All right, I will introduce myself. My name is Nikki Kruger, and I am the Director of Marketing and Business Development for Santa Fe Dehumidifiers. I am a HERS rater. I took Allison's HERS rating class.
2014.
Okay, there we go. You can see here on the left, I did get an award for tying for Simon Says Psychrometric Chart winner. I could not take down the other person as much as I tried. It started getting a little long, but I've been in the indoor air quality business probably almost 20 years now. I've encapsulated and installed a lot of dehumidifiers in attics, crawl spaces, basements, and HVAC systems. So heavily involved with ACA, also a lot of programs like Indoor Plus with the EPA. So a little bit about Thermistor. Thermistor is the company that manufactures the Santa Fe brand of dehumidifiers. Santa Fe is our residential brand for crawl space basements and also whole house ventilating dehumidification. We did have Ultra Air. That was our whole house ventilating dehumidifiers. And then probably about 3 years ago, we combined all underneath one brand. So we invented whole house ventilating dehumidifiers back in the mid-90s, and also were the first to market for the horizontal dehumidifiers used in crawl spaces. We also have Quest dehumidifiers, which is our commercial climate control, and then Phoenix restoration equipment we manufacture, and that is the equipment that's used a lot of times by restorers when there's hurricanes and other water loss events. So all of these products are manufactured in Madison, Wisconsin. And as you can see, we really focus on dehumidification. So just to get us kicked off a little bit here, so we're all talking the same terminology and concepts. So the sensible load in the home is the temperature that you feel, and that is often controlled by the thermostat in the wall. So the air conditioning and your heating, when it's too hot, too cold, you go over and you mess with the thermostat. The latent load is the moisture in the house or outside, and that is the moisture that is in the room that makes us feel uncomfortable. And we often say that the humidity level is high, or if it's wintertime, it might be too low where you live. And that is much harder to control with a thermostat. So a pint's a pound the world around. If we say a 70-pint dehumidifier, that is also could be interchanged with a 70-pound dehumidifier. So they may basically mean the same thing. And 1 CFM out equals 1 CFM in. And that's really important when we're talking about ventilation strategies, and also different pressures in the house, being able to understand how that those pressures affect our homes. So thermodynamics, hot goes to cold, wet goes to dry, and high goes to low. So this time of the year, we're definitely experiencing the outside trying to get into our house, especially if we're running air conditioning, making it drier in the house. Dew points are high outside, that air's trying to get in. High to low, if you're using an exhaust fan only, in your home, or maybe you switch on your kitchen hood or your dryer. As soon as you put that house potentially underneath negative pressure, again, all of that air outside is going to try to make its way into the house. So relative humidity is really important to understand that it's relative to a temperature. So if you look at our 3 circles here, the circles are all basically the same size. But what is affecting that RH percentage is the temperature of that air. So warmer air with that amount of water is going to be 43% RH. When you start cooling that air down, that RH goes up. So for every degree you increase the temperature, the RH goes down approximately 2%, and then vice versa. So if you're talking to someone and you say, you know, my relative humidity is 43%, it really doesn't mean anything unless we understand what that is relative to, which is the temperature. Now, dew point, on the other hand, gives us a better idea of really how much water is in the air. So when the relative humidity is about 100%, then we know that we're going to get condensation or the dew point. You look outside on a fall morning or a spring morning and there's water on the grass, that means the temperature has hit dew point. And dew point is really important when we start talking about potentially where we can have condensation, maybe in our crawl spaces, on our ductwork, in our walls, and understanding where that water is going to condense. So this is a great map. The gentleman that was part of inventing our whole house ventilating dehumidifiers, Ken Gehring, also known as Teddy Bear, on a forum called HVAC Talk, where he spends a majority of his time addressing moisture issues. He puts these dew point maps together and shares them with the team. And this map is from late September. And as you can see, the orange part of that map is where we're hitting dew points above 55 degrees. And typically when you start getting above 55 degrees, there's more moisture in the air that's coming in our house that can cause problems, especially in late September if we're counting on our air conditioning to try to maintain a safe and comfortable level relative humidity in our house. So you can see all the way up from the northeast down to Florida over to Texas, we've got 70-degree dew points outside. And especially in the Northeast, we're probably not running air conditioning. So always counting on air conditioning to control the relative humidity in our homes, and trying to maintain a 55-degree dew point is getting more and more challenging, and we'll talk about why that is. This is a great resource that you can kind of play with here on the left-hand side. This is from dpcalc.org. Again, that's dpcalc.org. And you can go in there and put in your temperature, your relative humidity, it'll give you your dew point. But what's great about this, if you go over on the right-hand side on my screen, the the third row down is mold risk. And basically you can mess with those parameters on the left-hand side and see when you're gonna have a potential mold risk. Really important for crawl spaces, basements, and even attics. All right, Allison, go ahead.
Okay, so this is a great quote. I love this quote. It's by Gus Handegord, a famous Canadian building scientist, and he says the three biggest problems in buildings are water, water, and water. We gotta deal with the water issues because that's one of the things that causes the most damage to buildings, and not just residential, but all kinds of buildings. So the biggest problem with humidity is I forget what I was going to say there. I had the same thing in Seattle. What was I going to say there? The biggest problem with humidity. Well, let's go into psychrometrics. I don't remember what I was going to say there, and I don't have my presenter notes. But anyway, psychrometrics. Let's talk about psychrometrics here. So this is the science of moist air, studying how dry air, which is all the components of air except for water vapor, and then water vapor, which is the moist part of moist air, and how these properties change with different conditions, and the psychrometric chart, which Nikki alluded to when she talked about taking the HERS rater class and tying with Ian Blanding, I think his last name was,
Yep.
for first place in the psychrometric chart, Simon says. So this is a psychrometric chart in case you've never seen it. There's a bunch of variables on here that you can look at, and this psychrometric chart is a simplified version. It does not have all of the possible variables. I think there are about 11 across the bottom. So moving horizontally along the bottom, you see degrees Fahrenheit. That's what we normally just call temperature, but it's actually the dry bulb temperature. Moving vertically, it says grains of water vapor per pound of dry air. That is basically the concentration of water vapor, how many water vapor molecules are in the air. And in case you're wondering about a grain of water vapor, how much is a grain? Well, it's this ancient unit. For some reason, they decided that a grain of water was 1/7,000th of a pound. 7,000 grains of water gives you 1 pound of water. Or as Nikki said earlier, a pint, because a pint is a pound. And then the curves on there, going back a little bit. The curves on there are the relative humidity, 10, 20, 30, all the way up to 100 on the left side there. The saturation curve, that's where it's 100% relative humidity, and that's where you hit the dew point. And the dew point, you can also read off this chart on the left on the 100% relative humidity curve. Okay, let's go to the next one so we can see how to use this. So when you move, so this is a good diagram from Don Gately's book called Understanding Psychrometrics. And you can see if you move from the center point to A, you are increasing the dry bulb temperature. So you're doing sensible heating only, which means you're only changing the temperature. You're not changing the moisture content. If you go from the center point to B, you're doing sensible cooling. Center point to C, you're doing humidification. So you're only doing latent heating. And if you move from the center point to D, you're doing latent cooling or dehumidification. Next. And when you're doing cooling and dehumidification, so when the air goes through your air conditioner, it starts at a point and it moves to the left first, it gets cooler, and then it hits the dew point and will start dropping vertically as well. So it changes in both temperature and humidity, and that's cooling and dehumidification there, what an air conditioner does. So here's a question for you. Think about it. Wrote it as group question, but since we are on a webinar here, we'll just throw it out there. So what happens if you have outdoor air with at 90 degrees Fahrenheit and 60% relative humidity, and it goes into a crawl space that is 75 degrees. So you take this, let's say a cubic foot of air, you take a cubic foot of air at 90 degrees and 60% RH, put it into the crawl space where now it cools to 75 degrees. What happens to the relative humidity here? Next. We can look at that on the psychrometric chart. So the first point, 90 degrees and 60% relative humidity is that first dot. Moving to the left when it cools off. Now the second dot on the left there that the arrow is pointing to is where we end up when it cools to 75 degrees. and now the relative humidity is up about 95%. So the relative humidity went from 60% to 95% just by bringing that air into the crawl space. And the importance of this, when we talk a lot about dew point, but relative humidity is the important parameter when we're talking about how moist air interacts with porous materials. And in a crawl space, for example, and in other parts of a house, we have a lot of porous materials. That's wood, concrete, drywall, all these things have pores in them, and water vapor can get into those pores. And it's the relative humidity that governs how much water from the air those materials will suck up. So next is another question. What happens in the opposite case? So that first question was about summer. Now let's look at what happens in winter. So we have outdoor air, 100% relative humidity, and 35 degrees. So cold, rainy day, let's say. And that air leaks into the house or comes in through ventilation. And we heat it up to 70 degrees Fahrenheit. What happens to the relative humidity this time? We can follow that path. So starting on the left with 35 degrees and 100% RH, move to the right to 70 degrees, and the relative humidity drops to less than 30%. So this is why leaky houses or over-ventilated houses, if you have one, have dry air in them. The air inside a house with a lot of outdoor air leaking in or being brought in will have very dry air unless you do something about it, because that cold air doesn't have much water vapor in it. When you bring it in, the relative humidity drops very, very low, and you can get dry skin, static electricity, chapped lips. You need lots of lotion. So that's what happens in winter. We say cold air is dry air. That's an easy way to remember that. Cold air is dry air. There's not much water vapor in it. Okay, so let's talk about typical dew points. Nikki showed that map, and that's a great map, the dew point map of the US. I look at that frequently, and it shows you what the dew points are like in a bunch of parts of the country, all over the country. So in the Southeast, next slide, we have pretty high dew points. It depends on where you are in the Southeast. If you are anywhere on the coast, along the, up the Atlantic and down Florida and then into the Gulf of Mexico, anywhere on the coast in the summertime, your dew points are pretty much above 70 degrees Fahrenheit most of the time, and sometimes even hitting 80 degrees Fahrenheit. So that can be a problem. This is a picture I took in Hilton Head, South Carolina, right on the coast, right on the water, and water's just dripping off the ducts in this vented crawl space. The issue here is what Nikki talked about earlier. We have air with the dew point, and dew point, by the way, let's point out, dew point is a temperature. So we always abbreviate it to just dew point, but it's actually a temperature. We're talking about a dew point of 70 degrees. That's a temperature. And then we have the other relevant parameter is the temperature of the surfaces that air is in contact with. If this air in this crawl space, on that day, it's probably at least 75-degree dew point. And all it has to do is find a surface that's below 75 degrees, and you're going to get this kind of condensation. Even with insulation on the outside of the ducts, when that air conditioner is running a lot on a hot day, if that duct is insulated to R4, even R6, in a very humid climate like this, you probably will have condensation dripping. And you can make it worse by putting two ducts right next to each other where there's not a gap, that gets cooler in there, and you get more condensation that way. Next. Okay, so this is another thing that happens. So this was a house that I was in where they had ducts running above the ceiling, and the ducts, this was a weird house. It had a finished room in the at the bottom of the house, and all around it was crawl space. Even like 5 feet above that room was crawl space. It was a very weird thing. They built this finished room in the basement. They had ducts running across it, and like in the previous picture, those ducts were sweating on the humid days, and this is what happens. And Nikki also pointed out in that dpcalc.org website, it'll show you the mold risk. Well, you keep things wet long enough and they'll start to grow mold. Next. One of my favorite pictures. And if you do really stupid things, like wrap your ducts in a vented crawl space with the wrong type of insulation, you're going to make it even worse. You can see the water droplets on there. There's one shiny droplet I can see at least. And that craft paper facing, this is like a fiberglass bat with craft paper facing on a duct in a crawl space. So very, very bad idea. And getting soaking wet in the summertime, staying wet, growing mold. Next. And that, when you have a vented crawl space and the unsealed floor above it, then in the house you get moldy shoes and moldy suitcases, and especially in closets, because the air doesn't move much in closets, and most closets don't have air conditioning vents in them to push dry air in there. So that kind of stuff can happen as well. Next. And here's another big problem in crawl spaces. Some parts of ducts are just not insulated. When you have a boot like this that's not insulated in a vented crawl space and they're doing air conditioning, that metal is going to get very, very cold, and that metal will drip water, and it will drip it right into that insulation jacket. What's my next slide? I don't remember. Nope. Okay, go back to the other one and let's talk about that. So I've been in crawl spaces where this metal boot going through the floor is just saturated with water. It drips, and it drips the water into that insulation jacket on the ductwork, and it will collect. That insulation jacket can be watertight, and you'll get a pool of water in the low spot in that ductwork. I've been in crawl spaces where I see this duct that looks like it's hanging pretty heavy, and I go and touch it, and it feels like there's a gallon of water in there. And I've also been in crawl spaces where I came after that happened, because eventually that duct jacket will break, and I've seen that as well. So next slide. This is again high dew point and a surface temperature below that dew point temperature. This is actually in Missouri about 6 or 7 years ago. This is I think this is Daniel Boone's very last house. And most people don't know this, but he had air conditioning. That's why you see condensation there. The window got very cold, and the dew point that day was, it was probably 78-degree dew point, I think. And this is the middle of the day. It was like 100 degrees, 78-degree dew point. It was miserable. Condensation on the outside of the glass on a summer day. Single pane, of course. The way to solve this problem is, number one, have good windows. Number two, maybe not keep the room quite as cold. I don't know what temperature they were keeping it, but if they were keeping it at 70 degrees or 68 degrees, which sometimes people do, that makes it more likely to have condensation. And with a 78-degree dew point, of course, you don't need, even 75-degree room temperature in there would have produced this. All right, next. And then there's this. This is actually a picture by Chris White in Baton Rouge. This is a hotel. They do a lot of mitigation work, and this was a hotel. And hotels are famous for doing things that really encourages mold growth in humid climates. They're getting better about not doing that anymore, but when they, so the exhaust in the bathrooms often is connected interstitially to all kinds of other places, like these walls. So if your bathroom exhaust is just sucking through a big cavity, and that cavity is unsealed and is connected to walls like this, and that wall is connected to outside, you're sucking humid air into that wall cavity. and both they've got the drywall off one side of the room. This is an interior wall. This is not an exterior wall. This is an interior wall. So both sides of that wall were air conditioned, and the drywall that they took off on this side certainly would have had the mold on it as well. So that's what happens when you put humid air in contact with surfaces below the dew point temperature and let that go for a while. You'll have a biology experiment inside your walls. Next.
Well, and that leads to me. Thank you,
Okay.
Allison. And we do have questions, so we'll come back to those at the end when I get through these slides. So what Allison is basically showing is, with all these photos and examples, is there's a lot of conditions and that can lead to moisture issues. So we've got tight houses. Basically, we're producing a lot of moisture inside that we're not getting out of the home. Leaky homes, we got it coming in. Construction drying is a big one. If we're in a area where we're getting a lot of rain and we're still building with those materials, and then we close up the enclosure with those wet materials, we're going to probably have some issues if we don't get them dry. Crawl spaces, basements, and attics, going to have issues if we're not addressing that outdoors making their way into those spaces.
Let me say something else about the construction drying. It's not just rain, because we put a lot of wet materials in there. When they finish the drywall, all that joint compound has a lot of water. If you blow cellulose into the walls, they mix water into that to make it stick better. Concrete has tons of water in it, and then that dries out into the space inside. So for a house on a slab, it's going to have a lot of extra moisture.
Yeah, and that's very true. And just even the condition of the wood without it raining. If you're getting a lot of wet wood on your sites, that's going to be an issue too. So lots of wood that is going to absorb moisture can be an issue. Low loads, meaning we're building a tight enclosure and we don't need a lot of air conditioning runtime, which is a goal ultimately. But if we're counting on our air conditioning to control that moisture 24/7, 365 days a year, depending on what climate zone you're in, there might not be enough AC runtime. Mechanical ventilation, if you are in a humid climate where you like that dew point map that I showed you, and you're bringing in outdoor air with high dew points, something's going to have to condition that air. We have higher SEER equipment that's really energy efficient, that has lower sensible heat ratios, and we'll talk about that a little bit more. Again, high dew points outside, mild temperatures, your spring, fall, overnight times when we're not running the AC. People generate moisture. And then probably one of the largest factors also is we can design homes and actually install the HVAC equipment perfectly. But once you put people inside and you give them control of that thermostat, all bets are off.
Yep, that's why I like to say that high performance homes need high performance occupants.
Yes.
You got to train them.
And that means everybody's on the same page, because what I like to keep the thermostat at and what my husband likes to keep the thermostat at, very different. So if you're trying to control the humidity in your home based on AC runtime, there are a lot of challenges with that. So home needs, there we go, lost control. Homes need dedicated dehumidification for comfort, health, property protection. Also, we're seeing a lot of partial and no load times, even at peak seasons in some of our homes, because we're building such high performance homes. We can't control human behavior, and really it's the only way to ensure 50% relative humidity. So people generate moisture. One person adds about 1/4 pound of moisture from breathing, and then another 1/4 pound from other activities, cleaning, cooking, showering. So if you have a family of 4, they can add up to 2 pounds or pints of moisture to a home per hour when they're home. So just the people alone generate moisture. And then we have other sources. We talked about the construction moisture and how much that can add. foundation, drywall, concrete, just like Allison was talking about. Seasonal storage effect. This one really hits home for me because my phone rings the most in August, September, and October with people seeing evidence of moisture issues. And that's because in the springtime, dew points start getting high. They're high throughout the summer. We're maybe not running as much AC as we need to control that relative humidity or that moisture. And then all of a sudden, August, September, and October come, and the materials in that home can't hold any more moisture. And that's where we start seeing microbial growth, is the seasonal storage effect. It just can't hold anymore. Now, winter comes, and if you have a leakier house that gets dry, or you're using a larger amount of outdoor ventilation in the winter time to help keep the house dry inside, then we can start drying. But if that's not happening, then we're just wetting, and we're not wetting and drying and wetting and drying. And we really need to have that drying forcing function in order to maintain the moisture levels in our materials. And then basements and crawl spaces. If you have a vented crawl space with no vapor barrier, you have a lot of moisture, but even that outside air coming into a vented crawl space is going to have issues. And basements, again, cooler spaces with concrete vapor pressure, you're going to probably need dehumidification in that space. So we've got high indoor humidity affects our health, comfort, our personal belongings, and the structure of our home. Maintaining a safe of 50–55% during the humid seasons is so important. It's not just an indoor air quality strategy for health, like potentially ventilation. A lot of times that's just a focus on more of our health. And some comfort as well. Stagnant air is not always comfortable, but when you're using dehumidification, you're getting all these benefits of using that dedicated dehumidification and keeping it at levels that are recommended by all kinds of organizations out there, whether it's American Health or the American Lung Association, ASHRAE, Building Science Corp. Everybody has ranges or levels they want you to keep them in, depending on the time of the year. So health and well-being is a big one. This chart shows all the different things, bacteria, viruses, fungus, dust mites, and kind of where they peak and where our optimum zone is. That 50% really is an optimum zone of keeping that relative humidity during the humid times. Dust mites. 80% of the population that has indoor allergies is allergic to dust mites. So if we can keep that level around that 50%, dust mites go dormant. So again, indoor air quality, very important, controlling that humidity level for health. Off-gassing is one that I don't think gets addressed enough. When the humidity levels are higher, the products in our homes, everything that we bring in, potentially that we have built with as well, will off-gas at a higher rate when the humidity levels are high. So if you ever heard of Chinese drywall, that was drywall that came in from China that made its way into the US. We saw a lot of evidence of it in Florida. And when it off-gassed, it caused formicary corrosion on our HVAC systems, refrigerator coils. And so we actually, Ken Gehring, who helped invent these dehumidifiers, was involved in trying to find a solution down there. And they did recognize that by using dehumidifiers and controlling the moisture in the air, the off-gassing was reduced greatly. Now that's not a solution at that point because homeowners just wanted it out of their house, but we also know that drywall made it farther north. But because the dew points weren't as high for as long enough period of time, causing the relative humidity in the house to be high, it was harder to find that drywall. So off-gassing is a really big one, that if you have somebody who's sensitive to the VOCs, that controlling that relative humidity really can help their health. So today's building practices, we're getting tighter houses. We're doing blower door tests. We are verifying that our houses are tighter. We're bringing in mechanical ventilation. Most of the building codes now, depending on what state you are, require mechanical ventilation at a certain air tightness in the home, depending on what state you're in. And then we're having lower sensible loads. When we make our houses tight, we don't need to run the heat or the air conditioning as much in order to maintain those comfortable temperatures in the home. We have very energy efficient HVAC equipment out there now, and we're seeing a greater need for dedicated dehumidification. So the goal of every energy efficiency building standard program out there is to build a tight envelope to reduce the runtime on the HVAC system to save energy. The HVAC system is, the largest system in the house of energy. So we want to reduce that as much as possible. So we tighten up our homes. And by doing that, we have more efficient, sensible cooling, meaning we get to that temperature very energy efficiently. But because of that, we're not running the system long enough in order to be able to remove the moisture that we need to. And the result is a lot of times where I run into situations where we start seeing evidence of microbial growth. We've got a case study on our website that was showing this happened in a multifamily complex in Virginia, where the resident was uncomfortable and she just kept cranking down that thermostat, and eventually we're overcooling, trying to control the moisture. And what happened was, actually, she wasn't the only one in this apartment complex. Within about a week, there were 5 apartments that had evidence of microbial growth all over the walls. So again, as homeowners, not understanding exactly how that thermostat works, we think it's our comfort control center. It's just typically temperature and not really focused on getting to that relative humidity. So we have higher SEER equipment. So it's very energy efficient at getting to that temperature on that thermostat. And we're seeing a lot of partial to no loads on our AC systems, even in hot, humid climates. So ventilation is one of those factors that we always have to look at when it comes to moisture in our homes. You typically have 3 strategies. You have exhaust, ventilation, supply, and balanced. If you are in a humid climate and using exhaust only ventilation, meaning that you've got a bath fan that's either running on a timer mode, continuous, potentially using an RH sensor to control that exhaust. A lot of times when I get called into projects that are having problems, they're using exhaust only ventilation. So when that's that 1 CFM out is 1 CFM in. When we're exhausting out of our house, we're sucking in from somewhere else. So we had a large production builder in the Mid-Atlantic who put in exhaust bath fans that had an RH sensor. And basically starting in the spring throughout the fall, those bath fans just never shut off because it was exhausting the moisture out when somebody took a shower, and it would run, but it was sucking in moisture from the outside to equalize that house. And so basically we were just bringing in as much moisture, if not more, that they were exhausting. So not a good strategy in humid climates during certain times of the year. Supply, that's where we bring in outdoor air in order to try to put a slight positive pressure. We see this more done in warm, humid climates. And then we have balanced, which is our ERVs and HRVs, where we're exhausting as much air as we are bringing in, and potentially on now we're seeing ERVs that you can actually bring in a little bit more air than you're exhausting to try to do that positive pressure to stop the infiltration. We've got and this is how that ERV works. So as you can see, they are not dehumidifiers. They have a core that's doing an exchange inside. So if it's drier inside than the air dryer inside than the air that's outside, when it passes through, it will exchange some of that latent or moisture. So we're not bringing in all of that moisture into the house. It will reduce the moisture load in the house, but it's always going to contribute to it. So it's not a surefire way to control moisture in a house in a humid climate. During the humid seasons, it will reduce, but it's always going to contribute. And we've got a case study that we did down in Orlando where you can see on the left here. Well, let's start with the right. This is using an ERV during a partial load time of the year. So rainy week, we're not getting running full AC at peak load. And basically the RH, which is the blue line in our family room, is following the dew points outside. We're consistently above 60%. And on the left-hand side, we went in, we took out the ERV, we put in a ventilating dehumidifier. So we're still ventilating, bringing in that outdoor air for ventilation. And then we just set the dehumidifier at 50, 55%. We don't care what that green line, dew points above 70 are outside. We're gonna focus on controlling the relative humidity in that home to a specific set point. So Armin Rudd did a study with the DOE, and basically an ERV is ineffective in keeping indoor RH controlled during the floating hours, which is basically when dew points are high outside and we're not running a lot of air conditioning. So overnight times, mornings, shoulder seasons, when the indoor and outdoor the difference between the indoor and outdoor absolute humidity is small. So again, we're humid inside, we're humid outside, not a lot of control with those latent loads. So sensible loads vary and latent loads typically stay uniform. So we've got a chart here. Here's how, I think this was in Houston. This is our outdoor temperature. You can see at 8 in the morning, we are at 74 degrees, and then the temperature at 4 o'clock in the afternoon is 98 degrees. The humidity outside, again, when we're cooler in the morning, the relative humidity is going to be higher, but then when the air warms up, the relative humidity is going to be less. But you can see here that our dew point, which is 71 degrees, remains the same. We have the same dew point. It's the temperature that is affecting the relative humidity. So you got to think about this when we think about when do we want to ventilate our home, because there's a lot of talk out there about possibly locking out conditions. Maybe it's too hot, we don't want to ventilate. Maybe the RH is too high, we don't want to ventilate. But to me, when I look at this chart and I think about, I mean, I always believe that you should ventilate when the space is occupied. If people are home, we should be ventilating. But here, if I had to choose a specific condition or time, I would probably ventilate at 4 o'clock in the afternoon, although it's 98 degrees and I'm going to have to condition that air, but my air conditioner is already running at this point. So why not bring in that ventilation air and get that conditioning from my AC that's already running? And then when the AC does shut off and the relative humidity is too high, there's still too much moisture in the air, then the dehumidifier can come on. So just something to think about when we're thinking about ventilation strategies and really trying to control our environments and keep them comfortable and healthy. So we have an app out there. I said we used to be, our ventilating dehumidifiers were underneath Ultra Air. We have this underneath Ultra Air. You can also find it underneath Santa Fe, which is an old logo that looks similar to the Ultra Air, but it's a brownish orange. But this app is very useful. The inlet is what the conditions are outside. So outside, I can put in it's 88 degrees, it's 65% relative humidity, and it's going to give me what my dew point is. The outlet is what I want it to be inside my house. I want it to be 74 degrees, 52% relative humidity, because I'm really going after that 55-degree dew point in my house, which is what ASHRAE recommends for in the homes during the humid season. And then below that, the flow is my ventilation rate. So I've got, you know, I need 100 CFM according to my ASHRAE 62.2 calculation for this house. How much dehumidification am I going to need in this home based on those outside conditions and what I want it to be inside? And this is telling me that I'm going to need 106 pints of dehumidification during that day. So whether that's my air conditioner doing it, my dehumidifier doing it, or at 88 degrees, depending on how much infiltration we have and what's going on in that house, the combination of the two. So it's a really great app just to be able to have on your phone, if nothing else, to know what the dew points are. All right. So my good friend Mike Barsek had put this together. He worked, and I forget what the gentleman's name is that put these together and gave Mike permission to be able to use them. But it's a really great visual just to kind of see what is going on with temperatures and dew points. So this is Atlanta, Georgia, and that first line is the bin temperature. So basically that's telling me what the temperatures are and then how many hours of occurrence the next line is, but those conditions happen throughout the year. The next line is the percentage of time. And the manual J design, which is at 92 degrees, the next line is the ASHRAE humidity design, which is 82 degrees. So basically that's saying at 82 degrees is typically when the dew points are the highest, but we're sizing the HVAC equipment in our manual J for 92 degrees in Atlanta, Georgia. So there's 10 degrees is a big difference on how we're sizing that HVAC based on what the latent loads are. So it's, again, when we size our HVAC equipment, we're using a manual J based on the peak load condition, which is 92 for Atlanta. Also, typically, how often we run at those peak load conditions are about 1% of the time. So we are sizing our HVAC equipment based on 1% of the time, and then we got to figure out how we're going to maintain that relative humidity throughout the rest of the humid season. So dehumidification strategies. We got single stage air conditioning, variable speed, mini splits, or a whole house dehumidifier. Our manual J wants us to design for 75 degrees and 50% relative humidity in the house. That is our bullseye. So AC, again, single stage, it's going to come on when the temperature gets above and there's a need for cooling in that house. Typically not going to run based on RH, although some of the newer systems will run a little bit longer in order to try to remove a little bit more water. But 70 degrees and raining out, most likely that homeowner is not running air conditioning, and that's spring and fall. And we can have extended periods of those conditions and we're not running air conditioning. So we typically need about 14 minutes of runtime to start effective dehumidification. So we need, Ken Gehring Teddy Bear typically says you want about 30 minutes of runtime in order to be able to actually collect the water on the AC coils, get it dripping down and out of the house. So ductless mini splits, I know a lot of them out there have that dehumidification mode. Again, These systems are focusing on smaller areas. Typically, it can get to that temperature really quick, but that dehumidification mode on a lot of these is just a timer based. And so you are just overcooling in order to try to dehumidify, which can create a very uncomfortable situation and potentially condensation. Variable speed slows that air conditioner fan down to remove moisture. Again, doesn't solve 70 and raining. This is a rusty register down in Florida, so we can get, you know, potentially colder surfaces. And the challenge with variable capacity, first of all, there has to be a load for it to run. But when it does run, it's usually so 2/3 of that capacity is still focusing on cooling, and 1/3 is based on removing moisture. And they typically have a higher operational sensible heat ratio, meaning that their dehumidification still is not that effective. So a whole house ventilating dehumidifier integrates with the HVAC system, and it can be set to a specific RH. So the relative humidity gets above your 50-55%, dehumidifier comes on and dehumidifies the whole home. It's the best option to help reduce homeowner complaints and warranty claims. We see a lot of new construction builders now using dedicated dehumidification just because it helps reduce the warranty claims alone on wood floors, cabinetry, paint peeling, that sort of thing. But it will help control mold, reduce odors, comfort levels are better, indoor air quality is better. Again, finished wood like the hardware floors will be more stable, and it also minimizes pests. So install matters. This is a big one. I saw that somebody actually had a question here, potentially on why an ultra unit would not be controlling the relative humidity to 60% or less. And a lot of times, first of all, that might be because the system isn't, the dehumidifier is undersized. And so it's just not big enough to handle whatever those conditions are that are contributing to the relative humidity. But install also. We always want to make sure that we're pulling from the return of the HVAC, or giving, better yet, giving the ventilating dehumidifier its own return, and then we tie in to the supply side of the HVAC system. There is a study out there by Florida Solar Energy released in July of 2018 that basically says if the dehumidifier is installed, the return to return, that it is the most ineffective and inefficient way to install a dehumidifier. I get calls from homeowners, contractors, builders saying we put in your dehumidifier 2 weeks ago and the relative humidity has actually gone up in the house. And one of the reasons for that is because it's been installed return to return. This will heat up the coils on the AC system, which will reduce the amount of water that air conditioner is removing when it's running. And when that AC is running, we want it to remove as much water as possible. The other thing is when that AC shuts off and there's water on those coils and the RH is high in the house, so the dehumidifier comes on, it's going to basically re-evaporate all that water that is left on those coils back into the house. And usually you have about a pint or a pound of water per ton of AC equipment on those coils. So 3-ton AC system, you've got 3 pounds or pints of water on those coils that potentially could get re-evaporated back in. So, and this is what that looks like. We've got a fresh air option here. We got the return air, and then we are dehumidifying and then going into the supply of that HVAC system. So crawl space and basements, you've got to control that moisture underneath the house. Potentially 50% of that air from below the home is going into the house. That carries a lot of allergens, mold, bacteria, insects, stuff like that. That air rises and we've got an indoor air quality problem. So one of the questions we often get asked about is energy use of a dehumidifier. I recommend that the residential energy dynamics calculator that they have for electrical usage. Basically, this is our 98-pint dehumidifier. I'm using it 270 days of the year. Out of 24 hours, it's going to run 20 minutes of every hour during the day. My kilowatt cost is 11 cents, and it's going to cost me $159 to run that dehumidifier for 270 days of the year. So, and when you add moisture control or a dehumidifier to the home, you should be able to increase the setting on that thermostat 2 to 3 degrees and feel just as comfortable or more comfortable than if it was lower. So it's Phoenix, Arizona versus Miami, Florida. When you control the relative humidity, you are more comfortable at a higher temperature. So in the words of Dr. Joe Steenbrook, you cannot energy conserve your way to dry. It is going to cost you money in order to control the moisture in that house. But it's how we make our houses healthy, comfortable, and we protect them. So key takeaways: houses are becoming tighter and requiring less air conditioning, yet our moisture loads are high. We don't want to just wait on our air conditioner in order to remove humidity. And again, houses work till you put people in them. You can't control how they're going to run their HVAC system. Commercial grade dehumidifiers reduce liability issues due to high relative humidity for builders. And people want homes that are safe, healthy, durable, comfortable, and efficient all the time. And that is what we have. I'll have this information again. This will be emailed to you. And then this is Allison's offer for the code for his home, for his book, sorry. I'm not going to sell your house here, Allison.
This is just available on our store, energyvanguardstore.com. If you try to use that discount code on Amazon or Barnes & Noble, it's not going to work. It's just energyvanguardstore.com. You get a signed copy when you order through us and $10 off through next Sunday.
All right. Let's see here. I think I answered Sophie's question, and that might be even Sophie, you and I can jump on to figure out maybe if that dehumidifier is not removing enough moisture. We can talk about why that might be. With dehumidifiers, we have recommendations. I think we have 7 different ultra units for whole house, and we've got 4 for crawl space or basement. We give very conservative square footage recommendations. Again, there's a lot that can go on in a house that we might need to take into consideration, but we're very conservative because there are so many variables. Our 70-pint dehumidifier, we say up to 1,800 square feet. Our competitor, double, triple that. In some houses that might work, but the reality is we want to make sure that we're providing more dehumidification that is needed. It's hard to oversize a dehumidifier, but easy to undersize. And so having a little bit of extra capacity, just because we don't know how people are going to live or every variable is important.
So let me add to that a little bit. Yeah. Ideally, yeah, you can't really oversize a dehumidifier the way you can oversize an air conditioner. But if you are tying the ducts of that dehumidifier in with the ducts of the air conditioner, then it is possible to dump way too much warm, dry air from the dehumidifier into the duct system and cause some comfort issues. I mean, the house is still going to dry out and everything, but if your dehumidifier is bigger, you're producing more warm air on the output side.
Yeah, potentially. I mean, it's still the same amount of BTUs to remove a pint of water. It might just not run as long. It's more of the bigger the dehumidifier, it is probably not going to be, it's going to use more energy in order to dehumidify. But yeah, we don't want to oversize, if we have 1,800 square feet, we definitely don't want to throw a 155 pint unit at it for sure. And we don't want to short cycle our dehumidifiers either, similar by doing that. It's always going to run to a specific RH, but getting a little bit longer runtime on that dehumidifier is a good thing too, than constantly short cycling it as well. What are your thoughts on the new SEER 2 ratings? Thoughts on IRA when customers chase free money without regard to subsible heat ratio? Allison?
So yeah, the SEER 2 rating is out, and I have not really dived into that yet. You know, things are different. I mean, the thing to keep in mind is, you know, SEER 2, these are efficiency ratings that are based on standard test conditions, not real world conditions. And they're only useful for comparing one unit to another unit. Don't try to extrapolate and say this is going to mean that I'm going to spend, you know, X amount of dollars cooling or dehumidifying. It's only valid in comparing one unit to another. So when you have SEER 2 systems, make sure you're comparing them to other SEER 2 systems, not SEER rated systems.
Does concrete ever dry out? How long does it take most materials from install to mostly dry? That's a lot of variables there. Concrete never completely dries, right?
Yeah, well, I mean, but yeah, because it's porous and it can always absorb water from the air, and it continues to cure, though. It gets stronger, you know, decades and decades. It just keeps getting stronger. It keeps curing.
Yeah, but it will, you know, I guess depending on your insulation around it and that sort of thing, it usually will always still be absorbing to some extent. Is the dew point map accessible online somewhere? Do you have that URL?
Yeah, hang on one second. It's US Air something. Let's see, here it is. usairnet.com and then /weather/maps. But I think if you just go to usairnet.com, it's probably, let's see.
So what, I'm just going to say, what RH set point do you recommend for whole house? I would recommend 50%. That's what we're running our manual J's for, is that 75 degrees and 50% relative humidity. I would say 55 to 50%. Crawl space, putting your dehumidifier in the middle of the room, of the crawl space if possible. That usually doesn't happen because you don't know where your electrical is going to be or where you're going to be able to drain your condensate. But I would set it at 55% in hopes that the farther areas don't go above 60. And we always recommend for crawl spaces to put some flex duct and get that dry, warmer air away from the front of the unit, so we're not potentially short cycling that dehumidifier and just creating a dry climate around that dehumidifier. But the goal is to keep it below 60 throughout the same space, same with an attic. Did you find that, Allison? Is it just that URL?
Yeah, usairnet.com. And if you go to just that website, at the top, click on weather and then current dew points.
All right, and I think we're gonna wrap it up there. We have some more questions, but maybe Allison and I can respond to these through some emails as well. But I just want to thank everybody for joining us today. If you have any questions, please reach out to us. I will go right back here. Here's our contact info. And again, you should receive this recording. And if you don't, let me know. Any last words, Allison?
No, thank you for all. Thank all of you for signing up and coming to see the webinar today.
All right, thanks. Have a great day. Stop. Did I stop it?